What if the secret to time travel isn't hidden in massive spaceships or cosmic wormholes, but in a realm so tiny it defies our senses? A world where particles dance in multiple states, communicate across vast distances, and challenge the very flow of time. Welcome to the quantum realm, the strangest corner of physics, where the rules of reality bend and time itself becomes a puzzle. Could quantum mechanics hold the key to unlocking time travel, reshaping our understanding of the universe? Get ready to uncover the secrets of the mysteries of quantum physics, where time isn't what it seems, and the impossible starts to feel tantalizingly close. Let's start with something familiar: time. It's the ticking of a clock, the rhythm of our days, a river flowing forward, linear, predictable, unstoppable. Or is it? For centuries, scientists thought they had time figured out. In the 1600s, Isaac Newton saw time as absolute, a universal metronome ticking the same for everyone, everywhere. Whether you're on Earth or a distant star, time marched on, unchanging. But then came Albert Einstein in the early 20th century, turning time on its head. His theory of relativity showed that time is relative. Near a black hole's immense gravity, time slows to a crawl. Zoom near the speed of light, and seconds stretch like taffy. Time and space, Einstein revealed, are woven into a four-dimensional fabric called space-time, bending and warping with gravity and motion. Yet even Einstein's revolutionary view couldn't prepare us for the quantum realm, where time becomes a stranger beast entirely. Here, the rules of classical physics break down, and time starts to feel less like a river and more like a kaleidoscope, fragmented, probabilistic, and full of surprises. Quantum mechanics studies the universe at its smallest scales: electrons, photons, particles so tiny they defy common sense. Unlike Newton's clockwork universe or Einstein's flexible spacetime, the quantum world is governed by probabilities. Particles don't have fixed positions or paths. They exist as waves of possibility, collapsing into reality only when observed. This is where time gets weird. Take the uncertainty principle, discovered by Werner Heisenberg in 1927. It tells us we can't know a particle's position and momentum precisely at the same time, but it also applies to energy and time. The more precisely we measure one, the fuzzier the other becomes. At the quantum level, time itself blurs, becoming uncertain, almost fluid. Then there's superposition, where particles exist in multiple states at once, like a cosmic coin spinning heads and tails simultaneously until measured. Could time itself exist in superposition, with multiple moments overlapping? It's a speculative idea, but it hints that time might not be as rigid as we think. And then there's quantum entanglement, what Einstein called spooky action at a distance. When two particles become entangled, their states are linked, no matter how far apart. Measure one, and the other instantly responds, as if connected by an invisible thread. Could this thread stretch not just across space, but across time? Let's dive deeper. Imagine two particles, born together in a lab, then sent to opposite ends of the galaxy. Measure one, and the other instantly mirrors it. No delay, no signal, defying the speed of light. This is quantum entanglement, confirmed by experiments like those of John Bell in the 1960s, who showed that entangled particles share a connection that classical physics can't explain. But what does this have to do with time? Some physicists wonder if entanglement could link not just space, but moments in time. Enter the ER equals EPR conjecture, proposed by Leonard Susskind and Juan Baldacena in 2013. It suggests that entangled particles might be connected by tiny wormholes, microscopic tunnels in space-time, like shortcuts through the universe's fabric. If true, this could mean entanglement is a bridge not just across space, but potentially across time, uniting quantum mechanics and Einstein's relativity in a profound way. Testing this idea is tough. Wormholes are theoretical, and creating them requires exotic matter we can't yet produce. But quantum simulations, powered by computers from IBM and Google, are starting to probe these connections, modeling how entanglement might bend space-time itself. It's a glimpse into a universe where space and time are more interconnected than we ever imagined. Let's shift gears to another quantum marvel, quantum tunneling. Picture a ball rolling toward a hill too steep to climb. In the classical world, it stops. But in the quantum world, particles can tunnel through barriers, as if passing through a wall without breaking it. This happens because particles exist as probability waves, with a small chance of appearing on the other side of an obstacle. Quantum tunneling isn't just theoretical. It powers the sun. In the sun's core, hydrogen nuclei fuse into helium, releasing energy that lights our world. Classically, they don't have enough energy to overcome their repulsive forces, but tunneling lets them slip through, making life possible. It's also behind technologies like semiconductors in your phone and the scanning tunneling microscope. Could tunneling apply to time? Some theorists speculate that particles might tunnel through temporal barriers, jumping from one moment to another. While purely hypothetical, this idea sparks questions about whether quantum effects could let us glimpse the future or past. For now, tunneling remains a cornerstone of quantum technology, but its temporal implications keep physicists dreaming. Now let's explore a mind-bender. Can choices made today influence the past? In the 1970s, physicist John Wheeler proposed the delayed choice experiment, building on the famous double-slit experiment. Fire a photon through two slits, and it behaves like a wave, creating an interference pattern. Add a detector to see which slit it passes through, and it acts like a particle, erasing the pattern. Wheeler's twist: what if you decide to add the detector after the photon passes the slits? Shockingly, experiments show the photon's behavior changes retroactively, as if it knew your future choice. It's not time travel, but it suggests the past isn't as fixed as we think at the quantum level. Then there's the quantum eraser, a variation that's even stranger. Imagine paired photons. One hits a detector, the other carries information about its path. If you erase that information later, the interference pattern reappears, as if the photon's past was rewritten. These experiments, conducted in labs since the 1990s, show that quantum measurements blur the line between cause and effect, hinting that time might be more flexible than we realize. This doesn't mean you can undo a bad decision, but it challenges our linear view of time. Could future technologies harness this to manipulate quantum states across time? It's speculative, but the implications for quantum computing and communication are profound. If delayed choice experiments weren't wild enough, meet retrocausality, the idea that future events can influence the past. In quantum experiments, measuring a particle's state now seems to affect its behavior earlier, as if time flows backward. It's like dropping a cup, then deciding later it didn't break. Retrocausality doesn't break causality or let us change history. It's confined to the quantum realm. Experiments by teams at IBM and Google have simulated retrocausal systems, showing particles can remain consistent across time without paradoxes. For example, a 2020 study modeled photons influencing their past states, suggesting time's arrow might bend at tiny scales. This could reshape how we view causality. If the future can nudge the past, is time truly linear? While macroscopic time travel remains out of reach, retrocausality fuels ideas for quantum communication and computing, where information might flow in unexpected ways. Enter Hugh Everett's many worlds interpretation. A radical idea from the 1950s. Every quantum event, Everett argued, splits the universe into parallel realities. Flip a coin and two universes storm, one where it's heads, another tails. Every choice, every measurement spawns new worlds. This solves time travel paradoxes like the grandfather paradox, where killing your grandfather prevents your birth. In many worlds, traveling back creates a new universe, leaving your original timeline untouched. David Deutsch, a pioneer in quantum computing, expanded this idea in the 1990s, suggesting time travelers could navigate parallel realities. But there's a catch. How do you find the right universe? With infinite realities, it's like searching for a specific star in the cosmos. And without evidence of these worlds, many worlds remains a mathematical marvel, not a proven reality. Still, it offers a paradox-free vision of time travel, igniting imaginations. General relativity offers another time travel clue: closed time-like curves, CTCs, proposed by Kurt Gödel in 1949. These are paths in space-time that loop back, letting you revisit the past. Imagine walking a circle that returns you to yesterday. But CTCs require exotic matter, stuff with negative energy we haven't found, and extreme conditions, like near a rotating black hole. Quantum mechanics adds a twist. The Novikov self-consistency principle, proposed by Igor Novikov in the 1980s, suggests that any actions in a CTC must be consistent with the present, avoiding paradoxes. Quantum simulations, like those run on Google's quantum processors, model particles in CTCs, showing they can interact with their past selves without contradictions, thanks to superposition and entanglement. While CTCs are theoretical, they hint at a universe where time loops are possible, if only in the quantum realm. Could we one day engineer such loops? The energy and technology required are beyond us, but the idea keeps physicists hopeful. Quantum computing is our bridge to these cosmic questions. Processors from IBM, Google, and others can simulate complex quantum systems, modeling retrocausality, CTCs, and entanglements effects on spacetime. But 2023 IBM experiment simulated a particle navigating a time loop, showing consistency without paradoxes. Google's team has probed entanglement's role in temporal dynamics, hinting at time ascension day times flexibility. Visual, a quantum processor glowing, data streams flowing. These simulations aren't just academic. They're steps toward technologies that could harness quantum phenomena. Quantum communication might use entanglement for instant data transfer. Quantum gravity models could reveal how spacetime emerges from quantum states, potentially unlocking spacetime engineering. So, where does this leave us? Practical time travel remains a distant dream, requiring exotic matter and energies we can't yet harness. But quantum physics is rewriting the rules of time. The ER equals EPR conjecture suggests spacetime and entanglement are linked, opening possibilities for manipulating spacetime's fabric. Quantum computers might one day simulate entire universes, testing theories of time and causality. Philosophically, these ideas challenge our sense of reality. If time is emergent, not fundamental, what does that mean for free will or destiny? If every choice spawns a new universe, are we living in a cosmic web of possibilities? And if retrocausality is real, could future technologies let us nudge the past in subtle ways? Skeptics argue these ideas are speculative, with no macroscopic evidence for retrocausality or CTCs. The energy costs of wormholes or time loops are astronomical, and many worlds lacks testable predictions. Yet quantum mechanics has a history of turning the impossible into reality. Think lasers, MRI machines, or quantum cryptography. As we push the boundaries of quantum research, we're not just chasing time travel, we're redefining reality itself. From quantum communication to space-time engineering, the future could be as wild as the quantum realm itself, a universe where time is not a barrier, but a playground. Quantum physics shows us that time is more than a ticking clock. It's a mystery, a challenge, a frontier. Whether we'll ever travel through time remains uncertain. But one thing is clear: the quantum realm is unlocking secrets that could change everything. So, what do you think? Is time travel a fantasy or the next quantum leap? The universe is waiting to tell us. Thank you for watching. If this journey into quantum time fascinated you, please like the video. subscribe to our channel, and hit the bell icon so you never miss a dive into the next great mystery of the universe. Until next time, stay curious.